When you finish this section, you should be able to 1. Recognize rational numbers. 2. Multiply and divide rational numbers. 3. Recognize variable expressions. 4. Translate verbal expressions into variable expressions. Rational numbers are numbers that can be represented as fractions, such as 4/5 or negative 15 over 21. A number can be written in decimal form and still be rational, as the following examples will illustrate. 0.75 is the same as 3/4. Negative 0.35 is equivalent to negative 35 over 100. Rational numbers can be represented in terms of terminating or repeating decimals. A terminating decimal occurs when the number has a remainder of 0. For example, 9/12 is 0.75 with a remainder of 0. A repeating decimal occurs when a series of numbers reoccur in a particular sequence or pattern, as in the following example. 6 divided by 9 is 0.666. Notice the bar over the last 6. This signifies that this number is repeated without n. There are 2 forms of rational numbers, fractional and decimal. There are basically 4 steps for adding and subtracting rational numbers in fractional form. First, find a common denominator, usually the least common denominator, which can also be represented by the initials LCD. Second, change all the components to equivalent fractions. Third, add or subtract the fractions and place the sum or difference over the least common denominator. Fourth, convert the solution to its simplest form. In order to add rational numbers in fractional form, a common denominator must be found. However, there is another issue that must be addressed before we go any further, and that is prime numbers. Prime numbers are numbers evenly divisible by only 1 and itself. Prime factorization occurs when a number is factored using prime numbers only. Each of the above numbers are represented as prime factors. Thus 10 becomes 2 times 5. 5 becomes 1 times 5 because 5 is a prime number. And 8 becomes 2 times 2 times 2. In order to obtain a common denominator for all of these numbers, simply multiply 10 times 5 times 8. Since we want the least common denominator, we will use a slightly different procedure. To clarify this, let's solve the above example problem. Now, one important rule to remember is that no prime number can be used more times than the greatest number of times it occurs as a prime factor in a single number. For example, 2 occurs 3 times as a factor in the number 8. Therefore, 2 can occur no more than 3 times in the least common denominator. Since 5 occurs only once as a prime factor in 10, it cannot occur more than once in the least common denominator. Armed with this information, let's solve this problem. First, use all the factors from the first number, which are 2 and 5. From the second number, use only 1. Since there are 3 2's in the third number, you are allowed to use 2 more in constructing the least common denominator. Finally, multiply all these prime factors to obtain the least common denominator, which is 40. Now each fraction must be converted so that they have the proper denominator. 4 times 5 is 20, and 8 times 5 is 40. The component is now 20 over 40. 2 times 8 is 16. 5 times 8 is 40. The component is now 16 over 40. Says 3 times 4 is 12, and 10 times 4 is 40. The new rational number is 12 over 40. The equation is now 20 over 40 plus 16 over 40 plus 12 over 40. which is 48 over 40. Now this problem can be further simplified. 6 times 8 is 48, and 5 times 8 is 40. Since 8 divided by 8 is 1, the equation becomes 6/5, which is 1 1/5. Adding or subtracting decimal rational numbers is very simple. Just align the decimals along the same vertical line and add or subtract according to directions. Thus, 3.245 plus 7.8 plus 0.001 becomes 11.046. There are 3 steps involved in multiplying rational numbers. First, multiply the numerator, then multiply the denominators. As the following example illustrates, 7 and 12 are the numerators in these 2 rational numbers. 9 and 49 are the denominators. Thus 9 and 49 are multiplied. Convert each of the numbers into prime factors and cancel all common factors. 7 is already a prime number. Thus we only have to convert 12 in the numerator, which is 3 times 2 times 2 is equivalent to 12. In the denominator, both 9 and 49 have to be converted into prime factors. 3 times 3 is 9, and 7 times 7 is 49. There are 2 sets of common factors in this equation, 7 and 3. 7 divided by 7 becomes 1, and 3 divided by 3 becomes 1. The equation now reads 1 times 1 times 2 times 2 divided by 1 times 3 times 1 times 7. Multiply the remaining numbers in the numerator, which is 2 times 2 is 4. Then multiply the remaining numbers in the denominator. 3 times 7 is 21. The final solution is 4 over 21. In order to divide 2 fractions, the divisor must be inverted and the division sign changed to a multiplication sign. In this problem, 3 divided by 45 is the divisor. When inverted, 3 over 45 becomes 45 over 3. Make sure you remember to change the division sign to a multiplication sign. The equation is now 4/15 times 45 over 3. Notice in this problem we have like numbers in the numerator and the denominator. Cancel all the common factors in the equation. Only 2 times 2 divided by 1 remains after the common factors have been eliminated. Say 2 times 2 is 4. 4 divided by 1 is 4. One of the key things that separate algebra from basic mathematics is the use of variables. A variable is a letter used to represent a number. X, M, C, N, Y, Z are examples of variables. Variables are used to represent unknown quantities. Using X as a symbol for multiplication is not recommended because it might be mistaken for a variable without proper spacing. A term represents the variables and numbers being added in a variable expression. Variable terms consist of 2 parts: numerical coefficients, which in this example is 5, and literal coefficients. X cubed represents the literal coefficient. Negative x times y times z. When a literal coefficient is preceded by a 1 or a negative 1, it is rarely written. X times y times z represents the literal coefficient. Negative 1 is the numerical coefficient. When variables are involved, no spaces are needed in order to symbolize multiplication. The lack of space between the numerical and literal coefficient represents multiplication. A variable expression is an expression which contains 1 or more variables. Variable expressions can consist of 2 parts: variable terms, which in the example below is negative 5x squared plus 15xy minus 3y squared, and constant terms, or just a constant. 12 is the only constant in this expression. A constant term is not necessary to form a variable expression. For example, if we eliminate negative 12 from the problem, negative 5x squared plus 15xy minus 3y squared is still a valid variable expression. Let's look at some more variable expressions. 12z plus 3y squared plus 4. If z equals 3 and y equals 1, the equation becomes 12 times 3 plus 3 times 1 squared plus 4. 12 times 3 is 36. 3 times 1 is 3. Now we have 36 plus 3 plus 4, which is 43. There are quite a few things you should know about variable expressions. For example, like terms have the same literal coefficient. For example, 8x and 5x are like terms. Simplify variable expressions by combining terms with identical literal coefficients. In this variable expression, 4y squared plus 7x plus 3y squared plus 2, the like terms in this expression are 4y squared and 3y squared. 4y squared plus 3y squared is 7y squared. The equation is now 7y squared plus 7x plus 2. This is the simplest form this expression can have without substituting values for y squared and x. Let's look at another example problem that's slightly different. Multiply each set of variables in parentheses by the numerical constant that precedes it. Multiply x squared plus z times 7. Which is 7x squared plus 7z. Multiplying negative 12z plus 5x squared by 3 yields negative 36z plus 15x squared. Next, combine the like terms. Thus we have 7x squared plus 15x squared is 22x squared. Next, there is 7z minus 36z, which is negative 29z. The simplified equation is 22x squared plus negative 29z. Next, let's discuss some simple properties of addition.